We will now look at mainly two spatial data decomposition methods often used to remove artifacts from EEG and MEG data. One of them is signal space projection, SSP. The other one, independent component analysis, ICA. And I will start with a bit of a high-level introduction to these methods, and then I will show how ICA works in practice, or at least illustrated in practice, using the ME Python tutorial. These methods are useful if artifacts have a characteristic topography. And that is, for example, the case with our eye blink artifacts. I mean, they have the strong, very characteristic positivity in the front around the eyes, because the eyes or the retina is a dipole. But it's also reflected in this very symmetrical or anti-symmetrical topography in the MEG and gradiometers in this case. And most eye blinks are the same topography-wise. That means you have a very stable topography that you can maybe remove. If you know this topography, you can regress it out of your data. The question is, how can you do that? And one way would be signal space projection. So if you are confident that you know the topography already, you can extract it from your data, and you want to remove it from your data, then that's signal space projection. But if you don't know the topography a priori, if you don't have some independent way of determining it, you can use blind source separation method. The idea there is that the method itself decomposes your data into meaningful patterns, topographies, and then you select the ones that you like and the ones that you don't like, and you remove the ones that you don't like eye blink topographies. There are several options, but I mean, they are related, but the one that is most commonly used for EEG MEG data is independent component analysis. But let's just briefly mention PCA, principal component analysis, and SVD, singular value decomposition, because I guess many of us are familiar with those methods from just general statistics. So these methods decompose your data into components that are orthogonal to each other. The first one explains most of the variance, the second most variance, and so on and so forth. And then these components are orthogonal to each other. ICA is a bit different. It also decomposes your data into a number of components, but they are not necessarily orthogonal, but they use another criterion for independence, which is more suitable for the kind of complex data that we usually have with EEG and MEG measurements. Okay, let's step back a little bit again. The general idea of these decomposition methods is always the same. So you decompose your data into a signal part and something that is noise with maybe some unknown amplitude. So imagine you know your eye blink topography. So you want to find out how much does this topography contribute to your data. And yeah, the rest is signal. So you only want to analyze the signal part. So you basically remove everything that you can explain in your data based on with the eye blink topography or the heartbeat topography, whatever you've got there. And this can work well with, for example, eye movements or blink artifacts, which are very stable for every eye blink, for every eye movement. But you somehow have to get these topographies first. You have to extract them from your data, or you measure them separately. So you ask your participants to move their eyes or to blink a few times. So that can be done. But you also have to be aware that if whatever you're interested in the data is highly correlated, if the topographies are highly correlated with topography of interest here, then you may also remove some of that as well. And that is a problem that you have with the other methods as well that I will mention. So PCA and SVD, very briefly, they do the same thing, except that you don't assume anything a priori about what is signal, what is artifact. So you let the method determine different components in your data, topography 1, topography 2, and yeah, they determine these components based on the variance that they explain in the data. The first one will explain most of the variance. The second one will be orthogonal and explain as much as possible of the rest of the variance, of the unexplained variance of topography 1, and so on and so forth. If you then think, okay, that these components reflect something meaningful, and you can define those that you don't like and separate them from those that you like, then you can recompose your data based on the good components, and you've got cleaner data. Okay, this is what I just said. Yeah, in this case, for example, I'm just assuming that maybe component 2 is a bad one. Well, I mean, I think you very quickly get the idea. So in this case, you also have an order of the components there. So in terms of variance, which may or may not be useful for you, for example, for exploratory purposes, sometimes you maybe just want to check, whether there's anything strange in your data. Maybe you want to just even use this component just to filter, the ones that explain least variance, the least variance, to remove some noise from your data. So that could potentially be useful in itself. But most of the time, actually, this is not really used to remove particular artifacts, because the orthogonality constraint is not really physiological. So unfortunately, eye blinks or heartbeat or so, I mean, the topographies they produce they're not always orthogonal to the signals of interest. So we may be able to do better by using a different kind of constraint than orthogonality. And this is what independent component analysis, ICA, is trying to achieve. And it's also often introduced as solving this kind of mixing of sources from different speakers or different musical instruments measured in different microphones. So every microphone gets signals from different speakers. So there's the mixing of the sources. But these speakers, don't necessarily do us the favor to speak with orthogonal sound waves. So it means if you use this orthogonality constraint, you still get a mixing of these extracted sources. But if you find the right measure for independence, not based on orthogonality, then you might be lucky, and you may be able to get the original signals back from the speakers. The question, of course, is, what is this magic independence criterion that will unmix your sources perfectly? And there's no unique answer to that. I mean, there are different kinds of ICAs around that use different types of constraints. And I'm not going to go into much detail here, but most software packages will offer you some versions of ICA that have been tuned to serve your purpose, to extract mostly eye movements and heartbeats from your data. If you need more information, then I'm afraid I can only refer you to the literature there. But ICA has proven to be very effective there. The idea is exactly like before: decompose your data. So ICA will decompose your data into different components, just with different criteria. So this is more or less what I've already talked about, but you just make different assumptions like PCA and SVD. Okay, I think it's better explained actually in maybe some real world example. Let's see, where do I have that? Here we go. So I'm now benefiting a lot from the tutorial in the MNE software package or Python package, which you will find online. So there's a lot of good stuff out there. But this is not a Python. These lectures or these online videos are not supposed to be about Python or MNE Python, but I think it's actually illustrates quite nicely, in this case, what ICA is actually about. Let's assume we have some raw data already, which we can then look up here. So here we are looking at some MEG channels, some EEG channels. You can nicely see that in the MEG, you have this very regular artifact, which is the heartbeat. And in the EEG, you have, we can see some eye blinks here, which doesn't mean that the heartbeat is only present in the MEG and that blinks are only present in the EEG, but it's just for illustration purposes here. So we want to clean our signal. We want to get rid of those. And first of all, we can extract and visualize these artifacts and look at them just to show that what the problem really looks like, or what the enemy looks like. So there's functionality to create epochs and average them based on the EOG channel, for example, in your data. So if you do that, well, you can plot your butterfly plot of all the channels in the magnetometers and here in the EEG. So you can see that eye blinks are very nicely present here in quite a few MEG channels. the topography at the peak is this anti-symmetrical dipolar pattern in the front. And with the EEG, this is a very characteristic positivity here in the front. So we just confirm that we do have EOG, eye-blink artifacts in our data, and this is how they look like. We can do the same for ECG in this case, create these epochs, average them, and look at a nice ECG artifact. It looks a bit more complex here. And yeah, this is the topography in the MEG. So it's usually the inferior sensors here at the border that are affected, but not just, but only those. Depends a bit on how the heart dipole is oriented. And yeah, this artifact is also present in the EEG. In order to then fit the ISA, it's usually recommended to high-pass filter your data. That does not mean that you then have to high-pass filter the data later as well. So this is only for the step of computing the ICA and determining the artifact components and to create the spatial filters that you apply to your data. So the final data set does not have to be high-pass filtered at 1 Hertz. And then you fit your ICA. And the one parameter that's important here, I would say, is the number of components. So ICA in itself does not determine how many components you should fit. So you have to specify that. There are different ways of doing it. And this is only optimized for speed now. So you should usually use a higher number of components. You can also specify this in terms of the explained variance. So how much variance you want to explain with your components in your data. So in that case, I would say up to 99% makes sense. So you may not want to go up to 100, but this is something that you should look at in other tutorials. So this is now optimized for speed. And then you can, when you've computed this decomposition, you can check how much variance you actually explain. So in the magnetometers, over 90%, in the EEG, a bit less, 77%. You can potentially also do that for individual channels or individual components, but that's not really that important right now. And then you can plot the sources. So every ICA component will have a time course. And you can just visually inspect these time courses, and you will see that in this case, conveniently, the first 2 components reflect the artifacts that we are interested in. So component 0 has these deflections here, which look very much like eye blinks. The EOG channel is also plotted here, so you can clearly see that they coincide with these deflections in the EOG channel. So this component 0, therefore, is very likely to reflect eye blinks, or at least the bulk of the eye blink. The second component shows the ECG artifact very nicely. So it looks like the 2 components, capture the artifacts that we want to remove. You can also look at the topographies of these components, and this confirms our hypothesis already. So component 0 has this anti-symmetrical pattern here in the MEG eye blinks. This topography with largest values here around the border. So this is very likely to be the heart. You could do that now for EEG as well. I'm not going to do that. And ultimately, you can apply ICA to your data and look at the result before and after. You can exclude the eye blink and then the ECG and see what happens. So in this case, before is plotted in red and after it's plotted in black. And indeed, you've clearly removed at least most of the artifact by applying your ICA. And I think this is, let me just check. So this was the EEG, exactly. This is the MEG here. This is now for the heartbeat. Okay, you can also plot more properties of the ICA components that can be useful if you have more complex situations, or maybe you're not sure whether or not you should actually remove any artifacts if you want to see how often and when the artifacts occur. So there are some tools to explore your data in a bit more detail, like of course look at this, the frequency spectrum. So in this case, we've basically in this tutorial, they've done us the favor to make sure we already know which components should be excluded. So it was the first 2 components that was very easy to do. You can then, if you want to exclude other components, you can simply do this by eye and basically tell the ICA which components to exclude, and then you apply that to your data. But of course, ideally, we want to make it as little subjective as possible. So what could potentially be an objective criterion to decide which components reflect eye blinks or the heartbeat? Well, you can look at the correlation between the time course of the different time courses of the different component with the time course of the EOG channel, or both, or the EOG, two EOG channels usually in your data. So you can do that here. So you can first of all find find EOG segments, and you can then check in your data what the correlation is. Oops, sorry, let me just find that. Yes, so what the correlation is between the time courses of your ICA components and the EOG channel. And in this case, there's a clear winner, component 0. We knew that already, but now objectively confirmed has a very high correlation with the EOG channel, so that should be removed. And there's nothing else really that is even close. So we can be reasonably sure that this one component captures most of the eye blinks. Let's see, is the same true for the heartbeat? So we can look at that for the heartbeat. And in this case, it also looks like component 1. And this has a very high correlation, so it will certainly remove a lot of the heartbeat. However, some other components at least have a little bit of higher correlation, at least, than we saw for the eye blink. So you might consider adding a second component. I will briefly mention that at the end again. So this basically confirms objectively that we did remove the right components earlier. But if you hadn't had any guess, if you don't want to do visual inspection, or if you have too many data sets to visually inspect, this is a way to do it. They also, in this example, explain that they did use a very low number of ICA components. If you actually use more ICA components here in your in your model, then you will find that you should probably model the heartbeat with 2 ICA components. So the heartbeat is not stable. It's not just one topography that stays stable. The heart is actually a dipole that moves over time and therefore creates more than one component in your data. So if you want to be really accurate, you should remove another component as well. Okay, I think I have just one more thing to say about more complex issues. So heartbeat and eye blinks are really easy usually to deal with. But just a few remarks. You may not have any eye blinks in your data. So some participants might be very disciplined, or maybe these eye blinks are always, outside the epochs that you are interested in. Maybe some participants really only blink, 1 or 2 seconds after they saw stimulus, so too late to actually be relevant. So that means you don't have to apply ICA all the time. So that's something for you to decide by inspecting your data, or maybe using some of these tools. And with the heartbeat, you also have to decide whether it's actually relevant to you. I talked about that in another session. If you have an event-related design within subject design, the heartbeat is probably not a big confound. So it's unlikely to differ between words and pseudo words, or living or non-living pictures, or something like that. But if you compare resting state activity between older and younger participants, then the heartbeat might be a confound, and you want to make sure that that's not the case. So you may want to apply ICA in that case. So you have to think about what type of artifacts you actually have in your data, which ones are relevant, and which ones you have to remove or want to remove first. And secondly, it is more complicated if your artifacts are a bit lower in amplitude, and saccades, for example, are an issue if you use more naturalistic experimental paradigms. For example, natural reading. So if you're asking your participants to actually read a sentence from left to right while you're recording EEG and MEG, your participants will move from word to word, or they make fixations forward, also potential fixations backwards, regressions. And this will, of course, be reflected in your data. So if you then look at the EOG or the EEG, so you'll see this nice little sudden jumps with every saccade. You can use ICA to correct these to some degree, but it is a bit more complicated than with eye blinks. I mean, this is just to illustrate how they look like. So eye movements to the left and right in the EEG have this anti-symmetric topography. In this case, it was an eye movement to the right. So the positivity occurs on the right of the sensor array or electrode array. With MEG, it looks a little bit different here, but not surprisingly, you get this artifact mostly in frontal sensors. I'm not going to talk in much detail about this here. I just want to say there are some papers on that. So by Dimigan, if you're interested in how to optimize your ICA for cases like that, then please have a look at these papers.